Although we do not discuss the cause of the change in the state of motion of bodies in kinematics, here we make an exception. In order to give a more detailed description on rigid rotation, we need to consider how forces are applied on rigid bodies. First, we demonstrate the theorem of transmissibility of forces by presenting a simple example, since the theorem has a fundamental role in the study of forces acting on rigid bodies. In the case of point masses, the effect changing of their state of motion is completely described by a force F acting on the point mass m, where the force vector has a given magnitude and direction. In the case of a rigid body, this information is not unique due to the size and extension of the body. In order to give a complete description of the effect changing its state of motion, we need to specify both the point P of the application of the force F, that is the point of the body where the force is applied, and the line of action of the force, that is the line along which the force acts. A system of forces simultaneously acting on a point mass can be replaced with the vector sum of the system. If the net force given by the vector sum is zero, that is the forces acting on the point mass are balanced, then they do not have an effect on the state of motion of the point mass. In the case of rigid bodies which are not point-like objects, the superposition and the balance of forces are more complicated problems, since the points of application of the individual forces are generally different. For example, let us place a board on 3 balls of the same size such that the balls rolling on the floor allow the board to move horizontally. If a pair of forces F and minus F, that is 2 forces of the same magnitude but opposite in direction, are applied on the board at the points P1 and P2, then the board either rotates about some vertical axis even if the net force acting on it vanishes, or stays at rest. The result is due to the fact that the lines of action of the forces are different in the first case and are coincident in the second one. The findings in this example can be formulated as follows. A rigid body under the influence of a pair of forces with the same magnitude but opposite in direction is in equilibrium if the lines of action of the forces are coincident. Then the pair of forces has no net effect on the body. Let us suppose that the force F is applied on the body at the point P1. We can also apply the pair of forces F and minus F at any point P2 on the line of action of the force F exerted at the point P1. Based on our statement, the force F applied at the point P1 and the force minus F applied at the point P2 do not have any net effect of the body, and they can be neglected. As a result, the force F acting at the point P1 can be replaced with the force F acting at the point P2. This result is expressed in the theorem of transmissibility of forces, stating that the point of application of a force acting on a rigid body can be moved anywhere along its line of action without changing its external effect on the body. The force acting on a rigid body can be translated along its line of action like the vector of angular velocity, which can be translated along the axis of rotation. In other words, the external effects of the force on a rigid body is independent of the point of application of the force along its line of action. The fact that the line of action is more important than the point of application has a crucial role when we determine how a system of forces acting on a rigid body can be replaced with an equivalent but simpler system of forces with the same external effect. This is the problem of the reduction of a system of forces, and we start the discussion of this topic with the analysis of some simple examples. First, we consider the superposition of non-parallel planar forces, that is, forces with intersecting lines of action lying in one plane. Let us suppose that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body. We translate the forces F1 and F2 to the point of intersection A of their lines of action, and determine their net force F by using the parallelogram law. Obviously, the point of application of the force F is arbitrary along its line of action. This result can be demonstrated by attaching 3 dynamometers to the points of application P1 and P2 in the intersection point A. The rigid body under the influence of the forces F1, F2 and F applied by the dynamometers at the points P1, P2 and A is in equilibrium, indicating the balance between these forces. If a third force F3 is also applied at the point P3 of the rigid body, we compute the net force F of the forces F1 and F2 and replace them with the force F. Then we can determine the superposition of the forces F3 and F in the same way as we did it for the forces F1 and F2. That is, we translate the forces F3 and F to the point of intersection B of their lines of action, and construct their net force F' by using the parallelogram law. We can repeat the same procedure for the force reduction if we add another force to the system of forces acting on the rigid body. We note that the 2 right-angled triangles with the sides D1' and D2' at the tail of the force F are similar because their angles alpha are angles in parallel lines. Since the lengths of the sides of the triangles formed by the parallelogram are equal to the lengths of the forces F1 and F2, we can write that the ratio of the length D1' to the length D2' is equal to the magnitude of the force F1 over the magnitude of the force F2. Furthermore, if the distances of the lines of actions for the forces F1 and F2 from an arbitrary point P on the line of action for the force F are denoted by D1 and D2, then the ratio of D1' to D2' can be written as the ratio of D1 to D2. By combining these two equations, we obtain the following relationship for any point P on the line of action of the net force F of the forces F1 and F2. The product of the magnitude of the force F1 and the distance D1 between the point P and the line of action of the force F1 is equal to the product of the magnitude of the force F2 and the distance D2 between the point P and the line of action for the force F2. We will use this relation in the analysis of rigid rotation. In the next example, we determine the superposition of parallel planar forces, that is, two forces pointing in the same direction. Let us suppose that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body. Due to the theorem of transmissibility, these points can be chosen such that the section P1-P2 is perpendicular to the line of actions of the forces F1 and F2. Although the lines of actions have no point of intersection, this problem leads back to the previous case if we apply the auxiliary forces F' and F' at the points P1 and P2 with the lines of action coincident with the section P1-P2, so that these forces cancel each other out. By using the parallelogram law, we can determine the net force F1' of the forces F1 and F'. Similarly, the vector sum of the forces F2 and F' gives the force F2'. Now we translate the forces F1' and F2' to the point of intersection A of their lines of action, and determine their net force F by using the parallelogram law. Since the force F1' is equal to the vector sum of the forces F1 and F', and F2' is equal to the vector sum of F2 and F', the auxiliary forces F and F' cancel each other out in the vector sum of F1' and F2'. As a result, the magnitude of the net force F is given by the sum of the magnitudes of the forces F1 and F2. The point of intersection O of the line of action of the net force F and the section P1-P2 is the center of the parallel forces F1 and F2. This center is always nearer to the point of application of the force that is the bigger one in the pair. If D1 denotes the distance between the points P1 and O, and D2 is the distance between the points P2 and O, then we can write that the ratio of the length of the section AO to the distance D1 is equal to the magnitude of the force F1 over the magnitude of the force F' due to the similarity of the triangles OAP1 and B1C1P1. Similarly, the ratio of the length of the section AO to the distance D2 is equal to the magnitude of the force F2 over the magnitude of the force F', because the triangles OAP2 and B2C2P2 are similar. We can therefore write that the length of the section BO times the magnitude of the force F' is given by the magnitude of the force F1 times the distance D1, which is equal to the magnitude of the force F2 times the distance D2. In another form, this equation states that the distance D1 divided by the distance D2 is equal to the magnitude of the force F2 divided by the magnitude of the force F1. We can generalize this result by translating one of the points of application of the forces F1 and F2, and conclude that the parallel forces F1 and F2 of the same orientation applied at the points P1 and P2 of a rigid body can be replaced by a net force F, which is parallel with the given forces and its magnitude is equal to the sum of the magnitudes of these forces. The line of action of the force F is determined by the position of the point O, where the length L1 of the section P10 divided by the length L2 of the section P20 is equal to the distance D1 over the distance D2. These two ratios are equal to the magnitude of the force F2 over the magnitude of the force F1, which can be written as the equation stating that F1 times D1 is equal to F2 times D2. This theorem can be demonstrated by using the apparatus shown in the figure where a light rod is suspended from two ropes through pulleys with some weights suspended from the other ends of the ropes. As a result, the forces F1 and F2 pointing upward are exerted on the rod at the points P1 and P2 through the ropes. The whole system is in balance if we suspend a weight G from the rod at the point O, where the magnitude of the weight G is given by the sum of the magnitudes of the forces F1 and F2. The forces F1 and F2 can therefore be replaced by the force F applied at the point O. Let us suppose that the forces F1, F2 and G are exerted on the rod by suspending 3, 2 and 5 units of weight respectively, and the distances D1 and D2 of the point O from the points P1 and P2 are 4 and 6 units of length respectively, as seen in the figure. It can be demonstrated that the system with such a setup remains at rest, that is the equation stating that G is equal to F1 plus F2 holds. Numerically, 5 units of weight is equal to 3 units of weight plus 2 units of weight. Similarly, the equation stating that F1 times D1 is equal to F2 times D2 holds as well, as its numerical form shows that 3 units of weight times 4 units of length is equal to 2 units of weight times 6 units of length. Now we discuss an example where we determine the superposition of antiparallel forces acting on a rigid body. First we consider forces of different magnitudes. Let us suppose again that P1 and P2 are the points of application of the forces F1 and F2 acting on a rigid body, where the magnitude of the force F2 is greater than the magnitude of the force F1. Here we can still follow the same procedure as described in the previous example. We apply the pair of the auxiliary forces F' and minus F' at the points P1 and P2 and determine the net forces F1' and F2' acting at the points P1 and P2. Then we translate these forces to the point of intersection A of their lines of action, and determine the net force F by using the parallelogram law. As in the previous example, we can translate the force F along its line of action and conclude that the magnitude of the net force F of the forces F1 and F2 is given by the difference between their magnitudes, and its line of action is determined by the equation stating that the magnitude of the force F1 times the horizontal distance d1 between the point P1 and the point O, is equal to the magnitude of the force F2 times the horizontal distance d2 between the point P2 and the point O. The force F replacing the antiparallel forces F1 and F2 points in the same direction as the force F1 since the force F1 has greater magnitude than the force F2, and the point P2 is located between the points P1 and O. In order to demonstrate this result, we can apply the same apparatus as used in the previous problem. The rope in the right-hand side exerts the force F1 upon the rod at the point P1, which is still one of the antiparallel forces, whereas the weight G acting on the point O represents the other one of the antiparallel forces. The net force of the antiparallel forces is a force that has the magnitude F1 minus the magnitude of G, and it is applied at the point P2 and points downward cancelling the force F2. The equation stating that the magnitude of F2 is equal to the magnitude of G minus the magnitude of F1 has the following numerical form. 2 units of weight is equal to 5 units of weight minus 3 units of weight. For the equation stating that F1 times D1 is equal to F2 times D2, we can write that 3 units of weight times 10 units of length is equal to 5 units of weight times 6 units of length. Now we consider antiparallel forces of the same magnitude. If the lines of action of the forces are not coincident, then we cannot use the procedure presented here because the lines of action constructed by applying the auxiliary forces have no intersection. 2 antiparallel forces of the same magnitude applied on a rigid body at different points forms a pair of forces. A pair of forces is the simplest system of forces that cannot be replaced by a single force. This fact can also be demonstrated with the apparatus. If we choose the weights in the suspension such that the force F1 is equal to the weight G, we will not able to find a force balancing the pair of forces. By applying the results obtained in these examples, we can determine the superposition of forces acting on a rigid body in the general case. Let F1 P1, F2 P2, ellipsis, Fn Pn be the forces acting on a rigid body at the points P1, P2, ellipsis, Pn. For the sake of simplicity, only the first 2 forces are shown in the figure. Now we apply the forces F1O, minus F1O, F2O, minus F2O, ellipsis, Fno, minus Fno at an arbitrary point O of the body. Here we also show only the first 2 pairs of the opposite forces. Since these forces cancel each other out, they have no effect on the rigid body. Then we determine the net force Fo of the forces F1O, F2O, ellipsis, Fno, which is applied at the point O. The net force F can be translated along its line of action and we write it without specifying the point of application. The rest of forces forms the pairs of forces F1 P1, minus F1O, F2 P2, minus F2O, ellipsis, Fn Pn, minus Fno. As a result, we replace the system of forces acting on the body with a single force and n pairs of forces. This procedure does not simplify the system of forces applied on a rigid body, but we will prove that the pairs of forces acting on the body can be reduced to a single pair of forces, and in turn, a general system of forces can be reduced to a single force and a single pair of forces.